And then the preferred committed the randomness, okay, into RA and RB. A and rho A, RB equals to RB vector and rho B. Okay, and two additional commitment. So I use the red pen. Oh, it's too. Come on. RA, RB. And check the randomness. Okay. Epsilon 0. And E1. Sorry. Okay. Okay, that's the first step. First step. Just right here, RA, RB. The 4 elements will be sent to verifier. And then verifier will reply C from the here. Yeah, and okay, this first step. This is the first step. Okay, first step, and then the third step. We will calculate a lot of Z. Z are the encrypted data. ZA is a vector, and the encrypted vector VA. So use the randomness RA vector plus C times A vector. ZB vector equals to RB vector times C. Yeah, and Z tau A equals to the rho A yes, tau A. Z tau B equals to rho B plus A tau B. And Z tau C equals to the epsilon 0 plus C times epsilon 1 plus oh no, cannot use C. Okay. Right. So C, and also in here we commit this the A, B. And here we modify the challenge to E. Okay. Okay, then we send the A, the B, Z tau A, Z tau B, and Z tau C. Okay, it looks quite similar to the protocol of product, right? Single product. Okay. But the differences are that we here we use the vectors, right? Okay, the equation of verification. The equations, there are also 3 equations for verification step. Like we'll put the ZA vector into box with the Z tau A as the blinder. If it equals to the RA times A to E. And ZB Z tau B equals to RB times A to E. Oh, sorry, B to E, B. And third is the, here I should use the right. The A vector, the B vector. Z tau C if equals to E0 times E1 times C E, sorry, E. C E to square. Okay. Okay, that's the protocol. Okay, first of all, help me check the completeness of the protocol. Okay, don't trust me, verify. So I stop here for about 5 minutes.
How many statements verified is going to select in this one?
Sorry?
How many statements verified is going to select in this one?
How many statements?
I mean, how many
Equations,
yeah.
here?
Like the sense that is that the tau A, tau A, tau B,
Yeah.
and tau C. So verifier will verify like all 5 of them, or yeah, like just pick any 4 or 3. With the first 4, will we be able to get? Yeah.
This one?
No, the
Which?
just this one. With these 4, if we do the another product, will we be able to prove this with just 4?
Okay. What's your question?
Yeah, I wanted to ask. If we don't send Z tau C.
Okay, Z tau C.
Yeah.
And then, what will happen?
We will be able to get this, verify this or not?
Yes, we cannot verify this because Z tau C is to fill this blank, to make sure that this equation blank, the balance.
Okay.
Yes. So yesterday we talked a lot about how to make sure that what the tau C, yes, sorry. Tau C is. So how to calculate tau C when we design this protocol? But now we have to pay more attention to the inner product parts. So why? So we can use the inner product to replace those single product to make sure, okay, this protocol works.
The hash of vectors is then like
the hash?
The hash of vector, the box of the vectors.
Do you mean hash?
I mean the box.
Okay, a box.
Like a hash, no?
Oh no, it's a Peterson commitment.
Huh?
Peterson commitment.
Okay.
So I write. Okay.
The box of the vector, what is it? Yeah.
Okay, so I write the definition here.
Yeah.
G1 A1. Yeah. H. A. Yeah.
So for me, this is a way of hashing.
Yes. Okay.
Yeah.
Okay. It's yeah. No problem. The hash with additive homomorphism. With additive homomorphism.
With additive homomorphism. That's what makes the end work.
Yeah.
We are using the same group for A and B both.
Parameters? Yes.
Okay.
Yes. But in practice, actually we can commit the two vector into one commitment in practice by using some technique. But here for simplicity, we just use the simplified version. Yes. G0. Okay, let me write down all the definition.
The H is a member of the same group.
Yes.
Member that we choose.
CRS, we have CRS and the G0, G1, Gn-1, and H from the Gn plus 1. G is a group. Okay. This is the parameter, public parameters for Peterson commitments. Okay, this the so what we want to prove is that the inner product of vector A and vector B equals to some value. For example, C. Let's use C to denote the inner product. And turns out inner product is very important. And the inner product also a bilinear map operation. So we can, in modern snarks, we can transfer or reduce many proving theorem into a bunch of inner products. For example, R1CS satisfaction and a matrix multiplication. I think a lot of operations from machine learning, so literally many matrix multiplication. And those operations can be reduced to a lot of inner product arguments. So if we can do inner product arguments, literally we can do anything. That's why it's always we can see many different approaches to prove inner product arguments, and the different optimizations, different techniques. So this one is the first that we can do that. We can prove inner product. Maybe next week we will show different ways to prove inner products over the KZG10. There'll be more approaches, more techniques. If anybody verify the companies, please raise your hand. Okay. Is it okay?
Yeah, I think it's right.
Okay. Good. And anybody else? Okay.
So G is also by hashes compute points generates.
Yes, and yes, by using hash point, yes. Okay, anybody else to verify the completeness of protocol? Please. Okay. Okay, all right. So, so right now the protocol is a little bit complicated. Looks scary. Now we just move, slower. Let me try to prove the soundness of this protocol by using extractor time rewinding. Okay, to prove why this argument works. Okay. Okay, to prove, we have to construct okay, here is a victim prover or honest prover, and we have a simulated verifier. We use V star as a potentially, so I'm going to hack P. So me as a V star verifier star malicious verifier, or not actually malicious, I'm just test if the prover is correct. So if P is honest or dishonest. So I'm going to construct the extractor algorithm to extract the witness, those are witness, and AB, and the result, because the result inner product also put into a box. I need to extract them out. Okay. So okay, the basic idea is that, so we first do the first round. So the prover will send RA, RB, E0, E1 to the to me, okay. And then I challenge E0, and then the prover, because prover is honest, so prover will send us a ZA0, ZB0, Z tau A0, let's use, don't use 0. Z tau B, Z tau C. And then here I will do a time rewinding, a time traveling to go back to the first step. After the time just right after the first step. And then the prover will not realize that the time is go back to the past. So I will send another challenge E prime. Then the honest prover will send me a ZA prime, ZB prime, Z tau A prime, Z tau B prime, and Z tau C prime. Okay. Right now, so like we talked before, me as the verifier star, V star, we can extract A and B from prover, right? Okay. So how? Because we can write the definition of ZB and ZA prime and ZB prime here. So try to figure out. So ZA equals to here, the RA, they are vectors, I remember that, RA plus E times A and ZB equals to RB plus E times, and yes, no, put it here. So for ZA prime, we have the E prime times A. We got those two equations. That means that the 1 minus 2, we will have Z minus ZA prime equals to E times, A times E minus E prime. And then we will have the A vector equals to ZA vector minus ZA vector prime over E minus E prime. Okay, we successfully extract A from prover. Okay, then we can use the same method to extract B, right? So right here, for completeness, ZB RB ZB prime RB plus E times. Okay. Let me. Okay, equation three, equation 4. So that 3 minus 4. Then we'll have the b equals to the e minus e prime, the zb minus zb prime vector. So, okay, easy, right? Easy. So the question that how can we extract this one? Okay, any ideas? I will stay here. Let's stop here for 5 minutes to figure out how can we extract this one from, because the inner product value is also a witness.
We have A and B already extracted, so we can multiply them.
Yeah.
No?
Yeah. Yes, you are right. But
We have to do the computation of multiplying.
we're not sure if this one is equal to
A dot B. Yeah.
the sum. Here the A, B. We just extract A and extract B, right?
Yeah.
So we do an inner product argument. We don't know if here the A and B if equals to here the C. We don't know that because we you know.
If the prover is honest,
Yeah, prover is honest.
it should be, you know, like it's not.
Okay. Okay. In the okay.
You said the prover.
The prover may not be honest.
Yes, okay. So,
Yes. So we have to extract the value from this box and verify, and we can prove that okay, the two vector we extracted is just equal to the inner product of those just equal to C. The C is C star for example, the value we extracted from the third box.
So
Here's
to prove C star is equal to C.
yes.
So I think you can try to get top C first, and you.
Yeah. Okay. Can you do that? Yeah.
I think another thing is maybe you need another round,
Okay.
and you will get one more like. Let me see.
But we don't know like epsilon 1 and tau c.
Yeah, but we have three. We have three. Can we solve top C from this?
Yes.
Like
And if we solve top C from this, we can do. We know G0, right? And we use this A and D we solved before. And we solve top C from this, and we check if this C star equals C.
Mm-hmm.
Does it work?
Yeah.
It's working.
Yes. Yes.
Okay. Yeah.
Okay. Okay. Good job. Good job. We need yeah. As Mark said, we just need a more round, more time traveling to because for this equation it's quadratic.
yet we have two variables, like we don't know the epsilon 1 and tau c, so we'll
Yeah.
equation.
Wait, so you need to do you need to do the commitment of a commitment? You need to commit twice?
No.
No, because is there a formula of the commitment inside the box. So it looks like you're committing twice. In the last line.
Which this one?
No, in the last line, yes. The last line.
This one?
Yeah, there is the box and then inside the formula of the commitment. So it's like it's doing commitment.
Okay, we don't have to do commitment here. Yeah, we'll just add more rewinding, and then we can extract C and tau C and all of stuff out of a box. Okay, let's try. Okay, let me check the equation. Yes. Okay. Okay. If we have a third time traveling, we'll get AA double prime, ZB double prime, Z tau A double prime, Z tau B double prime, Z tau C double prime. Then we can have yes, we'll have the ZA times Z A prime will equal to sorry. Let me check. Sorry, it's not correct. Okay, here I need 2 more minutes. We can directly extract C, the inner product of vector A and vector B. Let me figure it out. Okay, let me think. Yeah, yes. Okay, let me write this down. Yes, we can do that because we have the ZA, ZB equals to the A, B plus E times the cross term. Okay, the cross term. Just use okay, let me erase all of the stuff. Need more space. The RA B plus the RB A plus E square RA and RB, right?
It should should be RA, RB and E square times A dot B. Like ZA is RA plus EA, ZB is RB.
R plus.
So, like the first product will be RA times RB and the last product will be A dot B.
Here?
Yeah.
This term?
Yeah. Like ZA and ZB are this, so the first product will be RA times RB.
Oh yeah, yeah. Oh, sorry. Yes, correct.
Yes.
Yeah,
Yes.
it is constant term. Okay. Yeah, thank you for that. Then we'll have a similar equation that ZA prime and ZB prime equals to E prime square. A, B plus E prime RA, B plus RB, A plus RA, RB. Then use the so let the 4, 5 equation and minus that equation. We will have okay, these two terms cancelled out. Okay.
Yes.
And let's use the new notations. So okay, give it a new name. Okay. U. How about U? Okay. U. And here is the V.
Yes.
V. Now we can rewrite the ZA ZB minus ZA prime ZB prime equals to E square minus E prime square times V plus E minus E prime times U. Okay. Yes, this is correct. Okay. Then, so okay, here put it here. Okay. Because we have another round of time rendering that we have the A double prime, the B double prime equals to E double prime square times A B plus E prime, E double prime, and RA B plus RB A RA RB. Okay, 7, equation 7. And now we just get this equation by using 5 minus 6. Then we'll use the 5 minus 7. We got another equation. Okay, the ZA ZB minus ZA ZB double prime equals to E square minus E double prime square times V plus E minus E double prime times U. Okay. We got V, V, U, U. And then from the two equations, we can calculate, solve the the two equations got because they're linear equation, right? Then we can get the v. V exactly is the value inside that box, inside this box. Okay. Okay, let me write down the equation. Okay, here to solve this linear equations. Let me here. The v will equals to
We can rename the left side terms to make it easy.
okay. minus e double prime ZA ZB minus ZA double prime ZB double prime E plus E double prime minus E minus E double prime. Yeah, so we cancel. Here is the E prime minus. Okay. Yeah. We made it. Okay. Here's the V. We got a V. Okay. Yeah, we can also extract the U, right? Because we'll have V, then we can carry the V. The V is the cross term here. So literally, basically, we can extract all witness committed by the prover. So, okay, I think this extractor is special and useful for us to understand the power of extractors to prove, okay, this particle is sound. And we need a more. Okay, but here the simulator, the extractor is very. We have to understand that, because next step we will construct a more complicated extractor. Okay, I stop here for 5 minutes. Okay, 5 minutes. What time is? Yeah, we can offline check all the stuff. But so far, any question for the intuition or the basic ideas about the basic ideas. So it has a lot of no, not a lot of. A few the techniques that we combine them together, and all the techniques that we talked before. But yeah, I think it's not so easy to how do I say that? Okay.
I'm thinking that.
Yeah, give me the pen.
I'm thinking it right, because we already solved A,
Mm-hmm.
so we also got RA.
Yeah.
And we got RA, so we can compute it directly. We can compute this directly. And we know this, so we don't need this two. We can compute it directly.
Okay. Let me think. Okay, let me think. Yes, you are right, but yes, I think. Yes.
To get the non-commit method and using this commit to combine to extract the installation file. Like the concept from this method.
Yeah, the problem is that we have to prove.
The last, the bottom.
Instead of extract something out, we have to prove that the relationship. So the point here is that, yeah, good question. Yeah, very good question. I need to prove here that. Okay, the basic idea here is that because the equation is quadratic. Quadratic 二次方式. So then we have to do time running 3 times to using Schwarzschild lemma to. Okay, very good question. So yeah, let me try to remember something. It's quite a long time ago. Here. Yeah, good question. So we need to. I think by only this equation can we prove that the stuff is spread out is exactly boxing. Okay, the basic intuition here is that, so if we only use 5 and 6, so for extractor never touched this C box. So that's saying the value we calculated has nothing to do with the value inside this box. So we have to extract C by using this equation instead of only first. Okay, only first two. That's a basic intuition. So for extractor, okay, we first construct the extractor, and then we have to prove, okay, the value we extract out of the boxes actually satisfy the statement we want to prove. So that's also very important step. So in this example, we have to prove that the V exactly. First of all, V is inside C, and then we have to prove V equals to this one. Yeah. Let me. Probably I should use a different, a new set of notation to illustrate this idea. Yes, let me think. Okay, very good question. Yeah, yes. Yes, let me think. Okay, let me think. Yeah, yes. I think it's I need to check the proof.
This is one proving that the vectors actually exist.
We need to compute maybe like few times because it's not at least two times because it is vector. It's just like possible of that. And technically we can even do like n times, but it's useless because we just always want to prove that it's vector. We don't want to prove the other way.
Yes.
Depending on the formula to extract C, for me it's more interesting that I still don't understand.
Yeah.
Why extracting in the time travel proves something about the non-time travel world?
Okay. Let me try. Okay, let me.
What does it prove that we can extract in the time travel?
Okay. Extractor, the existence of extractor
Yes.
proves that if a prover can pass the verification,
Yes.
the verifier's verification, then the extractor always extracts something
Yes.
out of prover that the something that we extracted satisfy the statement that the prover wants to prove.
I consider the first term as stable, second is stable.
For me, this already proved that the verifier can verify, no? For me, the extractor proves that it's true the statement that the verifier is verifying?
Okay. The verifier, so if there exists an extractor, right?
Yes.
Then in the simulated world,
Yes.
then extractor can extract
Yes.
something out.
The knowledge. Yes.
And also in the real world,
Yes.
and then no extractor at all,
There is no extractor.
right? Because in physical world there are no extractor, but in physical world we assume there's no time traveling.
Okay.
And then the prover cannot distinguish about the two worlds,
Yes.
which world he's in.
Okay.
And then
That means
if
the
a
prover
prover,
cannot fake.
yes,
Okay.
yes, prover has no,
Way to lie.
Yeah.
If the prover
the prover will distinguish, will realize, okay.
Yes. The extractor is not possible. If the prover can lie, then the extractor
Will fail.
will not exist.
Yeah, does not exist.
Okay.
Yes.
If the prover can lie, then it's difficult to.
Yes.
Then the extractor do exist. The time traveling is not. Okay. It's difficult to visualize.
Okay, yeah.
He's trying to check if the prover is honest.
Yeah. The existence of the extractor proves that the verifier has to be honest. The prover is honest. Yeah. The existence of the extractor proves that the verifier has to. The prover has to be honest.
It's like if the verifier is
For me, that formula there already proves like if the prover is not honest, those formulas will not work. Why will it extract?
There's no point you verifying so prover has to be but
Yeah, but for me, it's like if the prover is not honest, but they can be honest. They can be honest like the prover is like choosing some R's or doing some tree, no?
Yes.
yes.
Okay.
It's choosing random values, but proof.
But they choose R because E comes after. I don't know what you can do. I don't know.
I think it's
You did? Okay.
question is
I'll catch up.
Nada.
1 milhão de pessoas mais que no mundo. Eu sou no pingando, assim, né? Eu preciso de um chat, o chat GPT e a foto. Eu entendi o que ele está fazendo, eu só não entendi o que ele está
What's that?
It's a
Equal.
define.
Because you don't know, yeah.
It's
Like
define.
that?
Or it's like you change it. Okay. Define.
Because you're
Yeah.
You have a lot of.
Yes. I'm sorry about that.
Use a lot there.
Yes.
We don't
Yes.
know
Yeah.
There are one thing that you do a lot, but I think that is clear, yeah. It's like that was the first time that I see it.
Oh, okay. It's a question mark.
When you.
Oh,
when you do it was the
yeah.
first time that I see it.
I see. Yeah. I should have explained that.
This one is like.
Okay.
I think that it's a part of the thing.
You can prove that Cooper, you can verify that Cooper is without knowing anything. But if you do it multiple times, you can be right. So that the secrecy is lost. Right.
All right. Okay. Let's go back to the second topic of today. Polynomial commitment. Okay. Because we already have an inner product argument, then we can build directly over this inner product argument to construct a polynomial commitment. Because polynomial evaluation is in fact a inner product. For example, we have a polynomial fx equals to c0 plus c1 times x, c2 x squared, blah blah to cn minus 1 times n minus 1. The degree of fx is n minus 1. Okay. And then we can commit f. So how do we commit f? We just use the c vector equals to c0, c1, cn minus 1 to represent the fx. Okay. It has another name that the coefficient form of the polynomial. So used in the coefficient vector. Then how to commit that the polynomial? We just commit the vector, right? Now because we use this machinery, so we just commit f defined as the commit c with a blinder. with blinder. Then, for example, if we want to prove that the f at some alpha, some point alpha, we actually will prove alpha. So actually we prove that the C with the alpha vector, the complement, the value of the inner product of C and alpha. So the alpha vector defined as so-called straightforward. The 1 alpha square alpha n minus 1. Okay.
Yeah.
Makes sense, right?
Yeah, makes sense. Makes sense.
But I think probably we leave that as a homework that to you, because in the original inner product arguments, actually B and the inner product value are also put into the box. But for polynomial comments, we don't have to do that. And the B vector is a public input, and also the inner product value. They are public inputs. So we can optimize this protocol, make it simpler. For example, our B is not necessary. We don't have to protect B. And we don't have to have the top B to protect the B, right? So the protocol will be much simpler, not so much simpler. It's simpler than this one. So okay, I'll leave this as a homework to you. And before next Tuesday, I will put the protocol put it in the DC channel. So if you have time, you can try to optimize it. It's easy. It's not so hard to. If you understand.
Ethereum shouldn't be equal instead of if only if, like f of alpha is equal to the inner product, no?
Sorry, what? Where?
F of alpha is equal to the inner product.
Yeah. Yes.
Yes, so it should be like equal instead.
Oh
of
yeah. Oh yeah. Yes.
So it's confusing.
Yes. Thank you. I'm not sure if we go further right now.
Yeah.
Yeah. Yeah. Next step, we will optimize this protocol. Okay. I think probably today we don't have too much time to. We'll just give some basic ideas of the next session. Okay. Because we don't have enough time today because it's more complicated. So why don't we use that this protocol or this simplified protocol for practice application? Just because. Look at this third step of this protocol. Okay, we have two vectors as the proof transcript. That means the proof size is O(n), right? At least 2n, 2 times n. We need smaller proof. We need smaller proofs. So next, we will come with some techniques to compress the proof size. So in the end, we will get the bulletproof O log n proof size. So it's bulletproof. Okay, the idea is we use more round. Here we use 3 rounds, and then we'll use O log n round. You can see the rounds will be log n rounds. O log n. For each round, the prover will compress using so-called split and fold techniques to compress the proof size. Half the proof size for each round. Then for log n round, we'll have the constant proof size at the end of, we got the constant size of a commitment, witness commitment at the final step. And then overall, we'll have the O log n proof size. Okay. I have to say that even bulletproof is not so popular today. But the idea of the split and fold kind of used everywhere. And also the bulletproof, there was some paper published probably 3 or 4 years ago that the people found that actually bulletproof has a very close relationship with the sum checker protocol. Okay. They have almost same algebraic structure. So I think we should do to do more work on the bulletproof. Then we'll quickly get the sum checker protocol idea. Then probably we can move on to the sum check and then go up and So I think today's time is enough. Yeah, if you have time this weekend, you probably can check out the bulletproof articles online. There's some very good written articles to read it first to get some intuitions, and then next session we will explore how a simplified bulletproof works. Okay. So yes. Other than doing split and fold, the bulletproof also combine those commitments into one commitment to make sure the proof size, the communication complexity is as low as possible. Yes, I think. Okay, all right. Thank you for your coming.
We are looking forward to the next class on Monday.
Okay.